to frame as much as possible and not capture
Yes,
the camera.
yes.
Okay, sorry folks, I'm just going to try and get this projector thing on the screen and then we'll get up and running. How's that sound? While I'm getting this all set up, you gave me a bit of an introduction. Maybe tell me a little bit about yourself, your program, and why you're in the course.
Yep. Okay, so why don't we start there?
A little bit about myself. I'm Cole. I'm a fourth year undergraduate student in computing science, a minor in business. I was told about this course, I think in my second year of undergrad. I knew someone who had taken it a few years ago and I highly recommended I take it. Looked into it a little more and tech, future of technology is right on my alley, so that's why I'm here.
Cool.
I'm Saloni. I'm a first year graduate student in the Department of Surgery. I'm studying islet cell transplantation. I took this course because some of the other courses within this group were included on our recommended courses, but none of those looked interesting. So in search of another course to take, I found this one and it definitely looked interesting to me, so that's how I ended up here.
Cool.
I'm Hannah. I'm also with the Department of Surgery, but I'm doing tissue engineered heart valve research. And I found out about this course from her. And after talking to Dr. Soles, I realized it was a pretty interesting course.
My name's Kevin. I'm in my third year of cell biology, and I took this course because I heard of some people who had taken it before, and they also recommended it. So I was pretty interested.
I'm Rebecca. My first year of medicine. Undergrad was in chemical engineering, and I took this course because it isn't recommended elective, but I've already satisfied my elective hours. So I'm here because I think Kim is very charismatic and he is really good at making presentations and getting really influential people to come and present. So I'm happy I'm here, okay?
Great,
Yeah.
thank you for that. Wow.
Right. Oh my goodness, that actually worked. This
Look.
is spectacular. And while you were all introducing yourselves, and not only did I get to hear that, I got to make this actually work. So, thanks. This is awesome. I really like, one of the things I like about coming, and I appreciate Kim continues to invite me to come back despite whatever job I do every time I do this, is that I really like that we do have a diverse group and that also we can focus on, okay, I do machine learning and machine intelligence research. I like that because of this group, we can actually focus on some of the higher level perspectives on what it really means for machines to think and not have to get essentially down into some of the specific details of exactly how they do that. Today we're actually going to go a little bit deeper into how a machine might think and make decisions in a world, specifically via technologies from reinforcement learning. But as shown here on the slides, we're not going to have any math at all because I don't understand it either. We're cool. Okay, before we do all of that, the usual question I ask, I think I'm promising Perils of AI 4 again this year, I think.
Yeah.
What did Osmar already tell you? What do you know already? This is like my usual first starting question. It's like, what don't I need to tell you because someone else has already told you and they do a better job than I do? The answer could also be nothing, and then I will just judge both Kim and Osmar.
Supervised learning. Sorry, that's supervised machine learning.
Cool. What do you mean by that?
So he taught us all about, obviously training data sets and then testing and he did mostly deep learning and categorization.
Okay, cool.
So beyond that, we haven't learned about unsupervised learning, but he did do a good job with introductory stuff.
Cool. Okay, and so when supervised learning, the reason I asked what do you mean by that as well is that someone else who probably will talk to you, Rich Sutton, likes to say that supervised learning is maybe better phrased as learning through labeled examples. And by that I mean you have some kind of example. Hey, I showed you a picture of Grumpy Cat. And then you want the system to spit out a label which is Grumpy Cat. The way that we train in what's usually referred to as supervised learning is you have sample label pairs. Here's the thing, here's what I call it. It's like, hey, that's clearly a banana. No, it's not a banana, it's Grumpy Cat. It learns from that error and updates its classification decision. So that's slightly different than what we're going to be talking about today, which is why I like to give talks like this at this course, because usually it's a good counterpoint to the learning through labeled examples. What we're going to talk about today is more specifically learning through trial and error. Before I do that, I just have to ask another question. Has anyone seen me do this particular one before, like Student DevCon or something like that? No? I'm not showing you slides and exercises that I was showing you? Okay, great. Good. Because we're also going to spend probably half of the time doing exercises, running around out in the hallway and actually doing stuff. Jumping jacks, push-ups, chin-up, no, I'm kidding. But we will be doing exercises out in the hallway. So we'll stand up and actually be a bit more active, and we'll learn a little bit about reinforcement learning through active participation today. So hopefully everyone's more awake than I am today and you're willing to do some active participation. If not, that's too bad, because that's what the plan is for the day. But let's start here. So a little about me first. I'm Patrick. I'm appointed over in the Department of Medicine, but for all intents and purposes, really, I'm a computing scientist. I study how machine intelligence is applied to bionic body parts, artificial limbs, replacement robotic parts for someone who has an amputation due to injury or illness. Our team looks at how we can develop new robotic technologies, make those technologies smarter and more adaptable, and then measure how effective they are with patients and inpatient outcomes. So really, it's all about intelligent assistive technology. That's what I do. That's what most of my time is. I also split my time with a company called DeepMind, our office here in Edmonton, and so looking at more fundamental applications of machine intelligence to human-machine interactions. So that's a little bit about me, which is why maybe you should trust me that some of the things I'm saying aren't complete garbage. They might be. I'll let you judge for yourself. But I'll show you first one example. This is if I can get to play on the little phone here. Yeah, it's actually working, believe me, unlike most robots. So this is a robot arm that we have in our lab just across the breezeway over in Kate's Group Center. It's arguably one of, well, probably not anymore, but at the time it was one of the most advanced bionic limbs on the planet. This is the output of the DARPA Revolutionizing Prosthetics Program. And what I'm hoping you to see through this video is that the arm itself is capable to a first approximation of making many, if not most, of the motions of a biological human arm. Some of them are made a little bit differently, but it can move through space, it can articulate fingers independently, and I mean, there's all the interosseous and lumbricals and things like that probably it can't do as well as we can, but for the most part, this is a fairly advanced robotic arm. It looks pretty fluid, it looks like a very impressive piece of technology. At the bottom of the screen there, we actually have some of our machine learning algorithms running in real time to predict and control the data stream. But all that isn't, oh, there we go. So maybe I was lying to you. Maybe it actually can do sort of like duckbill kind of motions. Okay. Either way, the important bit there is that for all of the impressiveness of that, this is my ex-graduate student Gotham Vossen now at Kindred Systems Incorporated, and you're seeing Gotham shake the hand of this robot arm. And one thing I think we can agree on is that's a pretty awful handshake. Like that is not at all like you go shake somebody like at a job interview or at a conference like that would not come off very well. And so for all that the robotic systems themselves are intricate and detailed and capable of fairly advanced motion when sort of moved in a pre-scripted or pre-recorded way, their ability to interact with a natural setting like a handshake is incredibly limited. So this is the motivating example I'd like to have for the day, because I think it really speaks towards one of the key questions that I hope you've already talked a lot about and I don't have to fill in, but why do we pursue intelligence, biological and computational intelligence? Why do we care about these things? And that handshake is one good example in that no matter how well we engineer that particular machine to do a really good handshake, and I know there's some wonderful researchers in Japan doing a great job on making very natural handshakes. That's a whole line of research. If you're really interested, you can go do that kind of research. It's really cool. But in a general sense, it's not just handshakes. It's machines interacting with a wide range of everyday naturalistic settings. Why intelligence? One is that intelligence gives a system, us or the systems that embody it, enhanced control over a really big, wild, squishy world. This is the world we live in. It's a pretty wacky world when you perceive it through the lens of a data stream. Intelligence also allows us or the systems that we create something that we've wanted since we were the dawn of a species, and that it allows us to see into the future, peer into a crystal ball, roll the knuckle bones of sheep, and try to figure out whether rain will come next season. Intelligence and machine intelligence gives us the ability to look into the mist of the future to some degree. And in particular, intelligence is one of the most powerful tools for solving problems. I mean, if we think about intelligence as the most powerful phenomenon in the universe, it's a Kurzweil quote, then we can think of intelligence as also a tool that allows us to solve very, very general problems. And that's why people care about this. People have been deploying machine intelligence in particular, and of course human intelligence and everything from finance to healthcare to transportation, self-driving cars, and retinal diagnosis of eye scans. Like our society has started to deploy intelligence to solve many of these problems, and especially machine intelligence. So that's why we might care about intelligence, why we would study intelligence, and why we might particularly study machine intelligence. I'm pretty sure you've already talked about. Osmar usually does an awesome job of rolling through why we would care about machine learning and AI. So then one of the next questions is, well, I mean, that was sort of like why machine intelligence? Solving general problems. We might want to anticipate the future. These are all great. But why learning? Like, can we imagine a system that might be intelligent but that might not learn? Nods. Okay. Maybe expand on it a bit. What would that look like?
Say like a browser or something like if you put all the information of Google into something, it didn't learn anything. It just has a ton of knowledge, which you can look at, but it doesn't necessarily know anything.
Yeah, like expert systems. The expert systems of the past are things even like Watson to play Jeopardy. You could think of some expert systems, not all of those. I mean, I don't want to say what everything's doing under the hood, but you could think about like imagine a machine that was fully omniscient. It knew everything. It already had all the possible facts or pieces of information or knowledge about the world that it could ever want, and you could just query it. Okay, maybe we could imagine calling a system like that intelligence. Not everyone would agree. Some people would say that you can't have intelligence without learning, but I think from a common perspective or a general perspective, people would say, yeah, that's a really intelligent system. So why might we care then about, specifically, why might we care about learning? I like to break it down to these three things that are on the current slide, and I'll walk through them one by one. One reason we might care about learning and not just intelligence, why specifically machine learning and machine intelligence, is that we might know, like as designers, as people trying to solve a problem, we might know what kind of outcome we want to have, but we might have no way to actually create that outcome on our own. Like in the handshake example, maybe we know what a good handshake looks like. We could put up like a little flag saying, yep, that was a really good handshake when we see one. But we can't, despite all of our engineering efforts, we can't actually engineer a way for that robot arm to give a good handshake. Like this is a fairly natural problem. We might be like, okay, cool. I would really just love to have the system go out and learn how to give a good handshake. And when it's done, I'll be able to check the box and say, yeah, that actually was a really good handshake. Other things might be design, like you have design criteria. You want a system to perform some function and you can measure when it's performed that function well, but you might not be able to, like you don't know how to actually build the system to do it. There's another related case, which is that, in fact, you do know what you want, but in fact, just scaling up, like let's say you know what you want and you also know how you might go about creating that thing. Like maybe you could engineer a really good handshake, let's just imagine that. But now, okay, maybe the robot got more complex, maybe the robot changes over time, and so it takes you 2 years to actually engineer like an entire master's thesis goes into figuring out how to do a really good handshake. And then someone comes out with a new robot. And you're like, no, now we have to spend another 2 years figuring out how to make a handshake, or even just a year building a good handshaking algorithm for this new robot. This is the case where things are really, really complex. We might know how to solve a problem, but scaling up to that problem is in fact really, really hard. We might know how to solve a limited example of a problem, but it would take so much time or so much effort to actually solve the full problem that we would hope that a learning machine can actually solve that problem. And the last one is in fact probably the most pressing and the most relevant to what we're going to talk about today, is that things change. I mentioned that robot arm might actually start to break down, or the fingers might wear down or something like that. Instead of having every time the arm change, which might be constantly, every day, all the time, or the person interacting with the arm might change, like you might be shaking its hand, or you might be shaking its hand, or Kim might be shaking the hand of the robot. Instead of every time a system changes having to go in and like manually tune all those knobs, get out the screwdriver and the keyboard and try and change the system, we would hope that systems can actually change themselves in real time during ongoing use. Much like your phone and your iPads and your computers are almost certainly changing their operation as you use them. Like, oh hey, you used those apps yesterday. Here, I'll give you those apps on the little selection screen when you open up your phone. Like, we hope our technology is doing this. And this is actually a really powerful application of machine learning. Learning thermostats as well. I'm not an expert in machine learning thermostats, but you can imagine some of the new thermostats that you could have for your house. You walk home and, oh, it's really cold. You turn up the heat. And then you leave and the heat goes down and no one's pressing buttons on the thermostat. It's totally reasonable to expect that, wow, your thermostat could actually learn when you press the buttons. When you press the buttons up and when you press the buttons down, and actually start to learn the patterns of activity in the house. Instead of going in and like doing the thing where you program in a schedule of heating and cooling for your house, the system could be able just to watch what buttons you press, remember it really well, and then just do that. It knows what day of week it is. It can even know in some cases, like if there was activity on your door cam. The more sensors and the more sensory apparatus you can install in the system, the better it might be able to do at learning your patterns of activity. But even that simple push button thermostat could actually adapt to the changes in your life cycle and the changes in your daily routine without you having to go in there and manually tinker with the scheduling. Is that cool? Does that like, did I make a compelling case for why learning might be important? Does everyone buy that? Okay, I hope so. You're all learning machines, so. Okay, awesome. And this is one of my controversial statements, which maybe or maybe isn't important to the discussion for today, but really like this is only more pressing now than it ever has been before. We're trying to solve problems, like even that thermostat problem that I just mentioned, where you might have a really complex changing schedule, is that our ability to actually directly engineer solutions to many of the problems that we care about as a species no longer scales up to those problems or the complexity of those problems and the goals that we're trying to solve. We actually are starting to need to put learning machinery, especially complex learning machinery in place to be able to solve some of the important societal problems that we're facing. So I'm sure, again, this has already been talked about in the course, but I just wanted to bring this up one more time, is that this is getting only more and more important, is that in some cases, for some problems, we just can't sit down and button mash until we have a solution to the problem. We actually need machines to learn solutions for us because of the scale, because of the complexity, because of the uncertainty. Cool? All right. So that gets us to reinforcement. Who knows? Do any of you know about reinforcement learning already? Okay, tell me about reinforcement learning. This is way better than me doing it usually. Tell me about reinforcement learning. You've got a diagram to help. This is awesome. It'll be even better.
Basically, just the agent will do something, and then you say yes or no, and then they'll take that yes or no into consideration, and then the next time they do something, it'll be different based on the reward they got the previous time.
Cool. Okay, so let's say that the system did something, and you gave it a reward. You gave it like a +5.5, whatever that means. How would you expect its behavior to change?
I would expect it to continue the behavior it did when we got the reward.
Cool. And if you gave it like a -5 or something?
Yeah, it wouldn't continue that, or would try not to, depending on what specific algorithm you're doing. It'll either avoid it completely or just put it on a lower down tier for it to try another time.
Cool. And what would it do instead? So like next time it comes around, it's like it said, oh, last time I did that, you gave me a -5. What would it do next time?
It depends what the goal is. So if it's just someone in space trying to get to a goal, and they went south one time, you told them, no, I don't want to go south, you need to go north, then they're going to try going north the next time.
Ooh, okay, cool. So we're getting a little bit into the weeds, but I really like this because I think you just said something that's slightly different. I think it's also really important. What you just said is that, last time you said don't go south, instead go north. As opposed to, I'm giving you a number that says what you did was bad. There was a demonstration or an active, so almost more like a supervised learning element to what you just said, which is like I told you what you did, I said this was bad, and I gave you an alternative. And so this is actually extending beyond what we might consider to be the sort of the firm ground of reinforcement learning. That's why it's great. I'm glad you actually did that, because this is a nice delineator as well. There's a difference between providing feedback, and that feedback has complexity and texture and detail to it, or demonstrations or suggestions, and giving a single signal of approval or disapproval. Okay, so this is one of the things that sets apart the foundation of reinforcement learning from many different forms of machine learning and machine intelligence, is that one of the premises, the sort of the reward hypothesis, is that everything that we mean about goals in the world is a single scalar signal of goodness or badness that we call reward. And the agent's job in the world is to maximize the reward it gets over the rest of its life. The expected future reward is something we call the return. So this is really important, is that reinforcement learning is all about the single signal of reward, and if we have goals, or there's something in the problem domain, there's something in the problem domain that is important, like the solution to the problem, is in fact encoded in this measure of reward. So that's the firm reinforcement formulation, and like you just said, it really involves an agent interacting in that world. This is important, because it actually is a stream of experience. That's one of the cool things that sets reinforcement learning or learning through trial and error apart from other forms of machine learning where you might just see like, here's an image, here's a label, here's an image, here's a label. Often the relationship between those two images is completely disconnected. There's no like, this image comes after the next image, and the decision you make on that first one impacts what happens next. In the reinforcement learning style problems, an agent is interacting in the world. There's this flow of interactions where the agent will take actions, and the world will then return to the agent some new observations, new state, and a signal of reward. So this is the loop of the reinforcement learning problem, where an agent will take actions in a world and perceive observations and reward from that world. And we call this the stream of experience. That's the reinforcement learning problem domain. It's fairly evident in most biological organisms. Do you have pets? Anyone have pets? No? Nobody's got pets? Just me?
Not here, just back home.
Oh, okay. But if you've interacted with a pet before then, I have a pet, he's a brown dog, he's quite wonderful. And like, he's trying all sorts of things out. He'll try like nose whistling at us while we're eating dinner to see if he gets some food, and usually he doesn't get some food unless one of the grandmas is there, and then like flicks some food to him, and then we scold the grandma, and the grandma learns from experience as well. Sometimes he'll be trying things out and he'll like run through prickly sticks in the woods and be like, oh, that was bad, I won't do that again. Or, oh wow, hey cool, if I do this when they say this, maybe I'll get a treat. Or if I stare really like this at the door for a while, I'll get my dinner. So animals interacting with their world do a really good job of acting within the world and then using the observations that they get back from the world and that reward to tune their behavior. So that's what we're going to talk about. But really this, if you take nothing else away from today, that's sort of the gist of reinforcement learning. But it really centers around learning to evaluate the value of different decisions you make in the world and then using that to change your behavior. Oh, that's the usual example. Never mind. There's the other example I could give. This is my son actually playing piano when he was a little bit younger. But it's very much a trial and error interaction. It's like, what if I hit this thing? What kind of noise comes out of it? Does this sound pleasing? Does this sound pleasing? It's like button mashing, using his thumbs to hit things. So organisms interacting with the world. I forgot I had the slide here actually. Right? So this is trial and error learning. And what's nice about reinforcement learning, the way that the reinforcement learning problem is defined, is that really it is a approach to natural intelligence. It's an approach using artificial intelligence, optimal control. People from operations research really love this. How do you optimize a process or a factory or a procedure? There's mathematical underpinnings as well. And one of the cool things is that the reinforcement learning framework really says that these are all kind of the same thing. Neuroscience as well, there's been a huge push in neuroscience to understand the mathematical framework provided by the reinforcement learning algorithms, the things that we commonly use, and use that to motivate how we actually study the brain. So there's always this really fruitful interaction between the neuroscience community and the reinforcement learning computational community. Reinforcement learning and decision making is studied across many fields. Some of the headlines, this is actually from an older slide of Rich Sutton's actually, is that RL is in fact now being widely used in some robotic applications. Maybe some of you saw technologies like AlphaGo, but reinforcement learning is fundamental to the entire revolution of solving the game of Go. As I said just a few minutes ago, that RL algorithms are actually the standard model for how reward is processed in the brain, the way that dopamine floods out of the deeper brain structures and changes the rest of the brain. This is following the process of temporal difference learning that has been really firmly established in the mathematical parts of reinforcement learning. And when we've seen, one of the I guess it's no longer recent, last decade, we've seen that when you put together reinforcement learning with the representational power of things like deep neural networks, there's been some really transformative applications, and a lot of researchers around the world, a lot of companies around the world are now showing some very impressive results when you sort of jam together the ideas of trial and error learning with the capacity of deep nets and more advanced computational systems to actually break down and represent aspects of the world. So this is really important. Okay, any questions or thoughts on that before we move on to a couple simple examples of decision making? Everyone's good? Okay, awesome. We have an hour and a half today, right? Is that?
We have an hour and 20 minutes.
Right? Okay, so I think we're still on time budget then. Okay, so I talked about reward, how you maximize reward. The systems are trying to actually maximize this single scalar signal that's called reward. To do this, I'm just going to show a really, really simple little decision-making problem, and then we can talk about this decision-making problem. to start out, you might imagine that you have some little intelligent system, and it's trying to learn how to act so as to maximize reward. And the intelligence system is the blue dot there, it's in the start state, and by pi, that little pi there, is something we call the policy, the way that it maps its situation in the world to actions that it might take, okay? So, as it moves to location 1, this poor little system is now faced with a choice. Does it go to location 2 or location 3? And the first way that we're going to talk about how it might solve that problem is how it might use models or values, learned or otherwise explicitly given, to make that decision. So right now, what should it do?
Depends on what the policy is.
Right,
Go to 2.
Go to 2? Okay, cool. So, I mean, in the absence of information, your policy might be, I don't know anything about these states. This poor little agent might want to just choose randomly or choose the first thing that it sees. Like, these are all totally reasonable, like, in this, the question I just framed, totally reasonable. So now let's imagine that we can actually have some information about location 2 and location 3. So now we have more information. Maybe you've already, were you looking through my slides online? Maybe you're looking through my slides online. Either way, now we look at the valuations. Let's call these values. They could be learned or they could be given. Location 2 and location 3. What should the system do? 2. Yeah, the answer is 2. Assuming that it likes money, then this is a very reasonable decision. Is that for this agent to go towards the larger expected future reward. In this case, it's 500, and we would expect that means that it says location 2, good, location 3, bad. Its policy might be to look ahead at the possible states that it could connect to, and choose the one with the highest value, and then clearly move to that location. Questions? Okay, this should be pretty yeah, of course, this is really straightforward, really simple. Turns out that this is pretty much the foundation of a lot of the problems in reinforcement learning. It's like trying to learn the values of different states and then build algorithms that can estimate those values, build models of how states connect together, and be able to do that simple thing we showed in this very, very simple world. So there's another way, so just to sort of bullet point that last example, that was an example of using values and some notion of how the world connects. Like, you have to know that from location 1, you can get to location 2 and location 3. This has to be something that the agent is able to perceive. And then it has to also be able to have some estimates or values for those downstream states. Some way of saying, yeah, actually I can say how much it's worth to be in location 2 or location 3. And what happens if there's 100 different locations you can get to from location 1? What happens?
Trial and error.
Yeah, cool. So you have to first, if you're learning those expectations, you're going to have to try out all those 100 options. That's one thing. And then if you have estimates for those 100 locations, you're going to have to probably search through all of them to figure out which one is the biggest. Okay, that's maybe 100 works. 1,000 starts to get tricky. What if there's an infinite number of things that connect to location 1? Clearly holding a value for each of them and searching through the values of an infinite number of possibilities is not something that any decision-making system can do in a reasonable amount of time. So it might have to do something else. And one of the other something else's you might imagine is that instead of using the reward or the things that a system learns to update the valuations of future downstream states or situations it might be in, you might instead use the feedback it gets, when you're saying, yeah, good or bad, or you should have gone north instead of south, using the reward feedback to change a policy, a way of behaving in a given state that doesn't actually impact, that doesn't take in as input anything about the downstream states. And we could call this using reward to alter or improve a policy. Okay, so the policy itself might be the thing that we now tune. And so what do I mean? What I mean by this is that instead of having to look at location 2 or location 3 or location 536, a system might simply be able to look at location 1 and where the state it just came from, and then be able to choose how to act based only on what it's currently seeing, based only on, say, location 1. In this case, you might just build up a probabilistic policy. Use reward to say, yeah, most of the times I've chosen action A versus action B. I've gotten good reward, so I'm going to choose to go action A versus action B, where A is maybe to go up and B is to go down. And so probabilistically speaking, you just start to choose which one of those places to go. Or it might just say always go to location 2. I've learned that, like, not that location 2 has a value and I look at that value and then choose, that from location 1 always go to location 2. It might be just simply a policy is conditioned on where you are, not the things where you might be. Okay, that's just another way of doing this, is that you could say, it's like you're running through the woods and like, do I run left or do I run right? Oh my goodness, I'm being chased by a tiger. It might just be like, okay, well, there's some rocks over that way and there's some trees over that way. I'm gonna go that way. That's if you can see the rocks and trees. Another might just be, which way is fastest away? I'm right here, how do I get away from the tiger as fast as possible? And you just act based on your immediate situation, not your look-aheads or your estimations of the value of future things. And it turns out there's ways to blend between those two forms of decision making, but one is modifying a policy that just takes a state and maps it to an action, and the other is doing that same process but by using the valuations of other situations or states. Is that cool? Any questions on that? No? Okay, awesome. I would do a demonstration, but it turns out that the reason I'm using my phone is that this laptop is completely out of batteries. So you don't get a demo, we get to be the demos ourselves, and we'll have exercises instead of me just showing you a little grid world example. But I think this is now time to actually go out and do things so no one falls asleep, including me. And what we're going to do first is actually learn how you might estimate. I showed you location 2 and location 3. There's values for those. How might a learning system actually start to estimate those values? Normally I have a worksheet, but I think I can do this in a much more streamlined way today because there's a couple of key things that we can do in this activity. But what I'm going to ask you to do is to, in fact, in groups of
2 or 3.
In groups of either 2 or 3, so we'll have you split up, to actually be a learning machine. We're going to try to have you be the estimator, and we're not going to talk about reward just yet. We're going to, in fact, just learn how to estimate the values of states and actions through raw sensory motor experience. So what I'm going to ask you to do is to, after we finish this quick briefing, I'm going to ask you to go out into the hallway, maybe take along a writing implement or one of your electronic devices, to go out into the hallway, pick a hallway, and answer just a simple question. How long is the hallway you're in? Okay? Now, the key thing is that I'd like you for this exercise to not use like range finding devices or measuring sticks. I'd like you to try to estimate how long is the hallway and communicate that back to us when we come back in the room using only the things that you have available with just your body. So I want you to say, like, to communicate how long is the hallway, okay? And while you're doing that, so you're going to be, clearly you're going to be doing some operations to try to figure out how long this hallway is. You're going to be maybe running some kinds of micro experiments for yourselves. You might think of it like that. But like, go find a hallway, stand in the hallway, and then try to estimate how long the hallway is using just your own meatware. And think also, when you're doing this, like we're going to come back in, so take notes. We're going to talk about it. Think not just your answer, whatever your answer is. Talk about your situation, like what kind of hallway you picked. I'll come out and walk around with you too. But then also, how accurate was your answer? What would you need to guarantee the accuracy of your answer? And any other aspects about really the certainty you have that your estimate is a good one. Okay, so that's the activity. So, break into, you want me to break you into groups of yeah, let's break you into, sure.